Right. Any questions regarding homework, exams? Nathan?
Can you do 3.6, number 20?
Hold on. Give me 1 second. Can't hear you. Try again.
3.6, number 20.
Okay. Dun, 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 dun. Dun, 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 dun. This one is going to be long. And I think more or less the problem you have will not be in the derivative, but how to type it in WebWork. Okay, but either way, we want to find y prime prime. Derivative of the inside. And I don't think there is anything I can simplify anymore, so I will just keep it that way. Yeah, maybe make it look a little bit nicer. Okay, step 1 done. Now for step 2, there's no shortcut. We have to use the quotient rule. Even if you apply the ln, it won't save too much trouble, I would say. So yeah. Okay, the derivative of the top, which basically means this goes to 0, this goes to a product rule. Derivative of x squared, keep the other, plus keep x squared, do the other. The whole thing times. Hold on. Okay. Times the bottom. Everything I just wrote down is the f prime g part. Now we still need the minus g prime f part. Now let's just copy this. Oh, here is a times 3x squared. Times the derivative of the bottom. Well, that's the answer. Good luck with typing. I remember you were a computer science major, so yeah, time to polish your skills. Is everything clear here for this one? It's a pretty nice structure, even though it's complicated. You won't see anything like this in the exam. Even if you can do it, I don't want to grade it. Okay, we must have something more reasonable. Okay, Nick.
3.6, number 9.
you have a choice. Do you want to use ln or not? This one has some production power and things like that. So I think this one is right on the edge. You can either do quotient rule or ln. So for illustration, I just do ln. But if you do quotient, I don't think it's going to be too hard. Then we will take the derivative. 1. So finally, y prime, I'm going to simplify this one a little bit, minus 2 cosecant square x divided by cotangent x minus 2x plus 1 divided by this times y. That will be a good enough answer. Technically, you can still simplify here, but we really don't have any preference here, so you can keep your answer that way. Ooh. By the way, one question I did receive from the homework is during office hours is, well, this is clearly how we do the derivative of ln cotangent. Meanwhile, you notice cotangent is nothing but cosine x over sin x. Right? Since it's a quotient, you can actually do an additional step, that is ln cosine x minus ln sin x. Now you have something a little bit easier. Make sense so far? If you want to do things in this way, feel free to do it, okay? I didn't verify, but it's actually very easy to verify this one, and this one will give you the same answer. And we really don't have a preference of which one over which one. Okay, so you either do it this way or this way. Okay. The beauty about the trick is you have a lot of identities. So you have a lot of answer which looks totally different, but when you start to simplify things, they become the same. They're definitely the same. So be confident. All right, Aaron.
3.6, number 1.
Log 2. So clearly this one is a chain rule. If you feel kind of shaky, you can first write down the formula for yourself, just for this log base 2, because it's kind of like less familiar. It's roughly 1 over x, same as ln, except you have this. Once you know that, that's for the log base 2 part. The rest is for this part. by the product rule. Sounds good? Okay, I would say in the exam, even if you kind of feel shaky, you can write down the step first, and I will give you partial credits of doing that. So this one shows you that you know the derivative of log base 2. Maybe you mess up with something after, but I know clearly where to minus the score. Okay, so more steps usually always give you a better chance for partial credits. All right, Adam.
3.9, problem 2.
A cylindrical tank. So this is related rate. We have a cylindrical tank with radius 5. No, 15 meter. Is being filled with water. At a rate of 8 cubic meters. Per minute. How fast is the height of the water increasing? Okay. Problem like this, always read first. Try to draw a picture if necessary to help yourself a little bit. Here's a tank. Okay. People are pouring water. 8 per minute. Okay. So as the water come in, the height is going to rise. You do it for a while, rises. Sounds good? All right. Always write down what you know and what you want. What you know is 8 meters per minute. That's the changing rate of what? I have to say that's the changing rate of the volume. The volume of the water in the whole tank is increasing as you pour more water in, and the rate is 8 cubic meters per second, per minute. What do you want? You want dH over dt, where h stands for the height. Okay. Of the waters in the tank. Sounds good? Once you have that, clearly you want to find a relation between V and H. So what do you know about a formula of the volume of a cylinder which involves the height H? Well, V equals base times height times height. And the base area in this case is a circle with a radius 15 meters. So it's going to be pi r squared times h. Okay. Well, over r is 15. Okay. If that is okay, this is the formula. Now you just want to take the derivative. Now here's the thing. You have r squared. Does this one go to 2r times dr over dt? Of course. The problem here is, does r change according to time? Not really. So dr over dt is 0. Okay, that means you don't have this term, or more precisely, this is the constant. Okay, therefore, I only need to write down this. dv over dt 8. So dh over dt. Answer. The height is increasing because it's positive, or rising at meter per minute. Sounds good. Okay, that's how we set up our related rates. I would say the first step is essential. You need to know which two rates are you trying to set up, and then you know how to find the equations, which two quantities you want to relate together. For this problem, it's actually not too interesting. I mean, you have a constant rate of 8, and your area stays as this, right? Then, of course, your height is as 8 divided by this. It's not changing. Make sense here? Constant rate of volume, same area, then constant rate of height. What's more interesting for you to think about is actually something like this. Well, it's not real, actually. You never have some tank like this. Maybe you have some tank like this, which is still not real, but at least it makes sense. Okay. This time, if you keep boiling water into it at a constant rate, can you see that as you go up, your area actually changes, your R changes? Okay, that would be more interesting. The changing rate of your dH over dt should decrease as your area becomes bigger and bigger and bigger if you have a constant volume pulling in. At first, it raises really fast. Okay, later it raises actually really slowly because your area becomes bigger. So that's a more interesting problem you can solve. But yeah, go look for some problem like this in the textbook. That's more interesting. You can actually have any kind of shape, like a Coke. Yeah, that's not a Coke, but roughly. That's a Coke bottle. There's fast, slow, fast. Okay, things like that. All right. Okay, TJ?
Yeah, can you go over 3.6, number 11?
611. We've done this before, so I will just write down the solution. And you stop me if you see anything that is that more explanations is needed. Y equal 2. Again, this one is right on the edge. You could do product rule. It's not too complicated. But since we're doing log, so it's all plus. Since we don't have dividing. 17. Are we good, TJ?
Yeah.
Sounds good. Okay, Aaron.
On the exam, as long as you don't specify, we can use either way, right?
Yep.
Okay.
Explicitly look for, did I say, please use logarithmic differentiation? If I say that, you need to do the log and do the differentiation. As long as I didn't say that, do whatever you want. Judging when to use log differentiation is actually a valid skill. Okay, so, all right. Adam?
For homework 3.9, problem 1, it says centimeters per second. Is it supposed to be centimeters per second squared because it's asking for the area that it increases?
Hold on. You're talking about web work, right?
Yep.
Okay, 1. Yeah, should be centimeter square per second for sure.
All right, thank you.
That's a very good observation. Yeah, usually people don't pay attention to units, but actually that's the most important thing in real life. So good training. Other questions from the homework? All right. Some question I received for a question like this. I will take an easier example. Something like this. Now we know we can take the log. Okay, and then we do the derivative. Such. And times y, whatever. All right. Now I receive a question from the homework that is like, why do you take ln? Because when you take ln, you're basically taking log, and you're very specific. You're taking log base e. Sounds good. The problem here is, can I use log base 2, log base 3, log base 10? Still okay? The question is, of course you can. Why? Because this property actually works for anything. It's not just for log base e. For any log, you can split a multiplication into a summation. It can be base 2, base 3, base 10. Okay, it really doesn't matter. The only difficulty is if you use something other than log base 10, log base e, your derivative won't be as nice as this. It will be, sounds good. And every time you do log differentiation, you are going to do the log differentiation here. Every time you take a 1 over x, now you just need to keep in mind, if you use any base other than e, you need to make sure you times ln2, if you use base 2. Sounds good? Okay, for that case, you can totally do it with other bases. Okay, it's just make sure that your derivative is a little bit more complicated, not dramatically complicated, more complicated. So when do you have advantage of doing that? Well, we have something like this. If you take ln, you will end up with Okay, but if you take log base 2, turns out the first one become easy. Make sense here? Since you already have base 2, why don't we just go ahead and take log base 2 so they cancel each other? You don't have any constant left. Sounds good? Okay, so if you see a lot of bases which are in the same base, if you take that corresponding base, your constant will look a little bit easier. The trouble is when you take the derivative of this, you actually have this. So whatever you saved from there will come back to you when you take the derivative. Okay, it will come back in the format of here. So I would say in general, actually ln it always work better. Even if you have some basis which is other than e, it looks nicer here. But then your derivative looks a little bit more messy. So it's a trade-off. All right. In 3.10, we did something called linear approximation. We give you a super fancy formula. Which turns out is nothing more than just finding the tangent line. Okay, so it looks nice, but it's just finding the tangent line. Which means you can either memorize the formula or you can just go ahead and find the tangent line, use your old way. They really return to the same answer. Okay, and that is called linear approximation. Let's do one more example, and we're good with that. Find the linear approximation of at x equal to 8. When you finish, use it to approximate. The cube root of 8.1, the cube root of 12, the cube root of 28. Like I said, it looks super fancy. Okay, you are looking for a linear approximation, but really, you are just looking for the tangent line at 8. Okay. Now, what is f8? That's cube root of 8, which is 2. All right. So the only thing you're missing is f prime a, which is not hard to do. If you feel confused, this is how you calculate it. So actually don't do this. I should use dash line. That's just some side work. Now I know Lx equals 2 plus Up to now, that's my linear approximation at 8 for the original function cube root of x. If you memorize the formula. If you didn't memorize the formula, just do the tangent line. You'll receive exactly the same answer. Question, Aaron?
When you say find the tangent line, you mean like y equals mx plus b and then take the derivative of that?
Do you have a point? Well, 8, 2.
Yeah.
Do you have a slope? Well, f prime at 8. So it's going to be 1 minus 2 equals f prime 8, which we just computed, x minus 8. Right. So you can see it's exactly the same process. Okay. So that's why I say, personally, for me, I never memorize this formula. It's just like not necessary. You just go ahead and do the tangent line. You got the same answer, and they're exactly the same idea. So the key is try to find this line. Sounds good? Once you find the linear approximation, basically what you're trying to say is, well, this is something I want to do, cube root, but it's too hard. Instead, I do this one, which is easier. Okay. So if you want to compute the cube root of 8.1, I can't do it. But I can compute the cube root, not the cube root, sorry. I can compute 8.1 if I plug it in L, which is way easier. And I got this answer, which is 2.0083333 ... What's the real answer if you plug in the cube root? The real answer is 2.008298. Okay. From here we can see, well, I'm not accurate, but I'm not too bad either. Starting from here, we start to differentiate a little bit, but my error is roughly like 10 to the negative 4, 10 to the negative 5. It's not bad. Okay, but this one is way easier. So I'm okay with that. Sounds good? Okay, with the same idea, how about we do this cube root of 12? You can see how easy this is. This is going to be 7/3 by my approximation. That gives me 2.333 forever. And the real one is 2.28942 whatever. From here, you can see, well, this one is still not too far away, but we start to differentiate starting from this digit. My error is bigger than what I just did for 8.1. If I use the approximation of this at 12, still okay? What about 28? What do you think will happen? It's going to be even more off. Since you're too far away from 8, I use all the information from 8. You want to do 28? That's basically ridiculous. Seven over 3, so 11/3. If I do this, 3.66. Actually, let's not approximate, but the real one -6.5. Kelsey, you're more off. Okay, so basically we have a very simple observation. The further you are from 8, the worse you are. If I'm trying to use this approximation to approximate 8.01, I'm going to be super accurate. 8.1, not so bad. 12, not good. 28, even worse. What if I use the information to approximate the cube root of 1200? That's going to be doable, number one, and it's going to be a disaster. But why don't we just do it? That's 100. Okay, what's that number? That's roughly okay, but what's the real one? From here you can see it's going to be super off because this is roughly 100. 100 to the cube is going to be 1 million. You're talking about 1200. Okay, it's way off. But it doesn't hurt to try it. Well, it's going to be 10.62. Sounds good? Okay. Why is that so? Well, very easy. I don't know the original function. Maybe it looks like this, roughly. I'm guessing from square root. Roughly something like this. Well, this is what happens at 8. What we did is, let me just draw this. At here, we're exactly the same, but at 8.1, the real value is here. My approximation is here, so it's not too bad. Sounds good. What happens to 12? Well, it's here. It's here. Can you see that the arrow become bigger? Okay, what about 1200? Well, one is going to be here, one is going to be here. The arrow is huge. From here, you can see basically what we're trying to do is we're trying to bet on a simple fact that is locally, you're roughly like a straight line, but only locally. If you just go too far away, there's no way I can guarantee you're still very similar to my line. But for a small period, it's going to work. Sounds good? So how do you make it better? Let's say if we did it for 28 and it's a disaster. Well, why do you have to do 8 for 28? You're very close to 27, and you know everything about 27, don't you? For cube root, right? So how about we do another linear approximation, but this time not at 8. We do it at 27. Now can you see, because you're so close to 28, your line become better if you do it at 27 compared to do it at 8. Okay, so that's the first observation. Basically, we can summarize to be the further away from A, the worse the approximation. Of course, the closer you are, the better the approximation. Okay? That means if you want to use this idea to approximate sine, 65 degree, which is something you don't know. What do you know? You know 45 degree. You know 60 degree. You know 90 degree. So you can do linear approximation at all these 3 places because they are easy. But my bet is going to be better do this because that's the one which is closer to 65. You will have the best approximation. The other two, they will work. The arrow is supposed to be big. The closer, the better. Sounds good? All right. Second observation. Well, it's not great. But if you want to approximate 12, you have to pick either 8 or 27. There's nothing in between that you know, right? It's either 2 or 3 for the cube root. There's nothing in between you know. Sounds good? So even though we already know this one is a bad approximation, which we just did, which is roughly like we're 0.05 off. Meanwhile, we already picked the right point. There's no way we can do a better point. 27 is not going to work. 1 is certainly further. Okay? So how do you still improve the accuracy? That's the problem. And that's what we mentioned last time. That's the moment you start to give up linear. You say, hey, linear approximation is great, but why not do quadratic? Okay, then your question becomes, why not do cubic? Or fourth, or fifths, or 100 degree, 1,000 degree, 10,000 degree. Why don't you just do that? Make sense to everybody? Okay, so we have a hidden assumption here. That is, the more degree we do, the better the accuracy. Can you justify that? Well, it's very simple. This time, let's call it AX because we don't know it's linear. Let's just call it approximation X. And let's talk about FX. What are you trying to do? You're trying to replace FX to AX. Why? Because AX is simpler. Still okay? Meanwhile, you also want this AX to be similar to FX. You don't want to change FX to some random picked AX. You want this AX somehow is similar to FX. Sounds good? Okay, so how do you do that? Well, I better make sure that you share the same function value. AA equals FA. For example, if your FX is like that, I better pick up AX, okay, which share the same function value here. I locally replace the black by the red. You can see this is a bad choice. But at least it retains some information. That is, at least it's better than this line, which doesn't even match you in the function value. Sounds good. How to make this one better? Well, we can require more. We can require not only you match the constant, match the function value, you also match the first derivative. So this line won't work because you only match the function value, but you don't match the first derivative. Still okay? By doing that, you already require this one has to be the tangent line, which is way better than the red line I just draw randomly, which just have the function value. Still okay? Okay. Can I do even better? In addition, I can require they share the same second derivative. Number one, a straight line won't work because a line can only retain information up to the first derivative. Any line you take the second derivative is 0. There's no way I can match your original thing, right? But if I use a quadratic, it's possible. I can draw a quadratic here, just say it, which will match your function value, which will match your first derivative, which will match your second derivative. So this quadratic is going to be very similar to fx compared to the linear because simply I retain more information. Still okay? All right. Can I do even better? I can require they share the same third derivative. From here, you know quadratic won't be good enough because quadratic don't have a third derivative. The third derivative is 0. You have to do a cubic in order to do this. Still okay? The problem here is as you keep increasing the degree of polynomial you for approximation, your approximation becomes better and better because you retain more and more information. Okay, for linear, you only retain these two information. You could do nothing beyond, including second derivative. For quadratic, you can include everything up to here, but not beyond. For cubic, you can include everything up to above here, but not beyond. So can you see that the bigger the degree, the more information you retain? And then, of course, the better the approximation, because the more similar you are to the original function. Does it make sense to everybody? All right. So in real life, if you want to do super good approximation, what do? Just take a very, very high degree. Okay. Now you see the trade-off. The more degree you take, the more work you need to do. Linear is easy. Quadratic is hard. Cubic is worse. Okay. It's more and more work, but you got a better and better results. Okay. So in real life, it's a trade-off you need to think about. Like, do you want it to be rounded to 6 digits? then probably a 7th power polynomial will do it. But if you want 11 digits to be accurate, you probably need to pump up to 300-degree polynomial. Okay, it's a dynamic trade-off. Okay, what if you just keep raising to infinity? Then basically the approximation function and the real function are the same. Why? Because you guys share all the derivatives you have. Then you are the same function. Good so far? So if you push this into the limit, actually eventually you can retain all the information. Then you won't have an approximation. You will have exactly the same answer. It's an exact answer. But you will push to infinity, which you couldn't do in real life. You can push to 1 million terms, but not infinity. Okay, that's how computer does stuff. That's how your calculator calculates all the function values you have. Your calculator can do sine 73 degree. How does it do it? Okay, it actually calculates a really, really complicated polynomial, however, okay, to get that number. Okay. Your computer does not know how to do sine. Your computer only knows how to do polynomials. Magically, polynomial is good enough. Think about it. If you have an electrical circuit, it's very easy for you to perform multiplication. Then it's very easy for you to do power. Then it's very easy for you to do power because you basically just repeat that thing for 100 times. You got the power to the 100. Sounds good? So for computer, representing power or polynomial is really easy. For computer, representing this is hard. Representing this is hard because any function can be anything, right? The beautiful thing is any function you write here can eventually be written down as a polynomial to very high degree. Okay. So as long as you can do polynomial, you're all set. The rest is just try to do a lot of them. Okay, people from computer science, this is basically just a giant for loop. That's it. All right. That's all we have from linear approximation. Everything I just talked about is just a little bit understanding, but really for exams and homework, you just need to know this formula, or even not this formula, just know you're looking for a tangent line. Okay. For anything quadratic or things like that, you don't have to, you won't be tested on that. It's just for understanding. Sounds good? Up to here, chapter 3 is over. Next chapter, we will be talking about applications of derivatives. We will find the maximum and minimum values, L'Hopital rules to find the new limit, and finally, optimization, which is a very, 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 very important application. Basically, you will be able to know how to find the best opportunity to invest, how to find the quickest time to go somewhere, how to find the cheapest way of doing some stuff. That's called optimization. Okay, you push it to the extreme. We still have 5 minutes left. I got this question from other sections, so I thought I should clarify a little bit. Sometimes people feel overwhelmed in the lecture. Which is totally legit because I write down a lot of stuff. We probably have 7 to 10 pages per notes per day for 45 minutes. That's a lot. Okay. So keep in mind, as you proceed further, your reading won't be faster, but you should be better and better at focusing your attention on the stuff which is important. For example, if I'm doing algebra, feel free to not pay attention at all because it's not the calculus. It's nothing new. If I'm doing implicit differentiation and I'm doing product rule and chain rule, don't pay attention to that. Why? Because you want to learn implicit differentiation. Okay, everything I just said is old stuff. You don't have to pay attention to it. Once you start to understand things to this level, you'll find every new section, you only have probably a few things to learn. Okay, even though there is a lot of information, but more than 90% of them are repeating what we did before. Sounds good? Okay. Your problem, of course, is try to recognize which part is the old stuff and which part is the new stuff. In order to do that, I suggest Do the homework on time. When I say on time, I mean the same day you finish the lecture. For example, let's say Tuesday you did this, Wednesday you did this, and Thursday you did this. You won't have anything on Saturday to do for 3.1 to 3.3 web work. Okay, so you have two approaches to do this. Number one, you wait until Saturday and do all of them. Okay, you will miss the office hour if that's fine. But the real trouble here is, as soon as I finish 3.1, I'm going to talk about 3.2, which quotes on 3.1, which quotes a lot on 3.1. Okay, as soon as I finish 3.3, I quote a lot on 3.1 and 3.2. Do you see the gap here? If you wait until Saturday to practice what you learned from 3.1 and 3.2, you won't be able to follow the lecture because everything looks new to you. Everything, including the old sections. That's why I say the moment we finish 3.1, you don't have to do all of them. Just do 2 problems, 3 problems from web work to get the basic of what 3.1 is about. Because tomorrow's lecture is going to quote on that. Okay, so just do a little, several, 2 to 3 problems. So instead of saving everything to Saturday, do it ahead of time. Will be way better. Sounds good? And trust me, you actually spend less time if you do things in this way because everything is fresh. You don't have to reread your notes before you start everything on Saturday. You just finish it today. So it's actually less time, equally distributed to multiple days. That's great. Number 2 is you should really do your review. I would say weekly, worst case monthly. What do? You take all the notes and all the web works you have done for this week. That's roughly, I don't know, 40 pages, 60 pages of stuff. What you need to do is you just need to rewrite all the notes in your way into less than 1 page. Sounds good? You learn a lot, but really a lot of them are redundant as before. There are only certain things you want to know, which is new. And moreover, you want to write the things down in your own way. That means you take in something, you copied it in your mind, you memorize it, and finally you produced it. You did some creative work. It's hard. You will find this is really hard. But that's where real learning happens. That's where the only place real learning happens. That is when you try to reproduce some stuff. Otherwise, I teach you a lot of things. Maybe you have good memory. You can totally get 100% in the exam without knowing anything because they're so similar to web work. Sounds good? To really understand something, you should be able to reproduce it. And finally, the ultimate challenge. Not everybody will do it. Talk about it. It may sound ridiculous, but ask yourself this question. What is calculus? Okay, what is calculus 1? What is derivative? What is limit? What is implicit differentiation? Why is it different from ordinary differentiation? What is quotient rule? Why is it necessary? What is chain rule? Why it works that way? Make sense so far? If you start asking yourself these kind of questions, you will find it's impossible for you to answer it in a short time with only a few sentences. That means you don't understand the stuff. You remember too many things which are not necessary. You're not clear with the big picture. You're not clear with the logic behind it. Sounds good? So if you really want to learn something well, you need to ask critical questions. You should stop feel good about what you just did because you did 100 homework. You should feel good when you finally feel like I understand this stuff because I'm not afraid of any question you throw at me about this topic. That means I understand stuff. And you should try that for all your classes. History class, biology class, chemistry class, you should try it for all your classes. Okay? If you don't know what question to ask, very simple. Ask the title of the section. If this section is about implicit differentiation, what is implicit differentiation? That's a question to start. Okay, what is related rate? Think about it. How do you answer that? What is related rate? Okay, you see your knowledge gap here? You couldn't answer it. not in a neat, clean way that you're proud of. But if you do it for 5 or 6 times on yourself, you will have an explanation which you're proud of. That's when real learning happens. Okay? Cool. That's all for today.